This demonstration is going to go through how to graph a system of linear inequalities. And the reason why this demonstration is being done is from my experience in teaching Algebra 1 and even Algebra 2. And the graphing of linear inequalities is oftentimes one of those topics that there are some teachers who just minimize and sometimes a bit too much. So some of you may have various experiences with it or lack of experience with it. So we're going to go over a couple of things. And one of the things you want to keep in mind is we're not going to go through how to solve inequalities. Again, that's a skill that you are expected to still have from Algebra 1 days. And if you have any particular questions about that, make sure to bring those up in class as well. But one of the things that you want to keep in mind is when you're solving inequalities, and you're going to see there's going to be sometimes you need to solve for one of the variables, keep in mind that if you need to multiply or divide both sides of an inequality by a negative value, that will switch around the inequality symbol. So you need to keep that rule in the back of your head at times as you sometimes work with this. But generally, if you're graphing a system of linear inequalities, you're not doing much more than you did when you were graphing linear equations. If you have it in slope-intercept form, you're going to plot the y-intercept, you're going to use the slope, you're going to graph. How the graph is going to look when all is said and done, that's going to depend on the inequality symbol, because there's going to be some shading, and you have to determine whether or not the line you're going to draw is going to be solid or dashed. So when you look at the first line here, y is less than or equal to 2/3 x plus 4, well, you're going to graph it the same way. You're going to start up at 4. You're going to go a slope of up 2, right 3, up 2, right 3. And you're going to draw that line. But there's a couple things you got to keep in mind. Because it's an equal sign here as well, it's going to be a solid line. So because it means the line is included as part of this. So if both sides are equal, that works. And if both sides are equal, that's what the line represents. So you're going to have a solid line, and because it's less than or equal to, you're shading below it. Anything below this line makes this true. So like a point like 0, 0, is 0 less than or equal to 4? Yes. If you put 0, 6 in, you're going to have 6 over here and a 4 over here. That's not true. That's why it's not shaded. Now, the decision about where to shade above or below is much easier when you have it in slope-intercept form, because of the fact that a less than means below, a greater than means above. If you have it in a form that looks like this, don't automatically think it's going to be shaded above just because you see a greater than sign here. You really have to wait till you put it in slope-intercept form, and I do recommend that you do convert to slope-intercept form. So for this one here, we would subtract x from both sides, divide both sides by 2. Now, luckily here, nowhere during the course of this solution process was it necessary for me to multiply or divide both sides by a negative, so it remained a greater than. That means I'm going to start at a y-intercept of negative 1/2, which might be hard to judge here. So you could even find another point on this line, for instance, like even look at the original one, x equaling negative 1 and y being 0 would be a point. So I can even start here and then realize the slope of negative 1/2 would go down 1, right 2, down 1, right 2, down 1, right 2. But as I draw the line, it has to be a dashed line, and because it's greater than, it's going to be shaded above. So far, this would be a solution to the inequality for these two, because this region here makes both of these inequalities true at the same time, whereas anything that falls outside does not. One last inequality here, negative 2 is less than x, which is less than or equal to 3. You can look at this as x is greater than negative 2 and x is less than or equal to 3 if you want to, and do them separately. But you know the x's should be between negative 2 and 3, not including the 2, including the 3. As you graph that, you're going to have two vertical lines, and you're going to be shading between them. And so it's this region right here that represents the solution set for this system of inequalities. And sometimes it's better to shade them lightly enough that you could just darken this and say, well, this is the solution. One of the things that's usually called is a feasible region. The feasible region represents all ordered pairs that satisfies the system of inequalities. So, some things that would be considered solutions. Anything that falls in the shaded region, like 2, 1 here, that would be a solution to the system of inequalities. Anything that falls on an intersection, as long as both of these are solid lines, it works. But as long as it falls on a border of this region, like here at 3, 1, that's a solution. This one up here, 0, 4, that's a solution. So all of those would be solutions to this system of inequalities. Now let's talk about some things that would not be solutions. And going back to the original graph, before we just showed this region here, even though there's some overlaps, there's some areas where 2 of these inequalities overlap each other, like here and here and here. If all 3 do not overlap, it's not a solution. So some things, and of course, obviously this region that isn't shaded at all would definitely not be a solution. It doesn't satisfy any one of them. So some non-solutions, one would be, of course, like -8, 2. It doesn't satisfy any one of these. But one like this here, 5, 4, it satisfies these 2. It doesn't satisfy this one. So, and you can see that still falls well outside the feasible region, so it's not a big surprise. Now, you also have to keep in mind that anything like this that falls on the border and it's a dashed border, it's not a solution, because 1, -1 here would make both sides of this one equal to each other. Well, I don't want that. I only want it to be greater than, so that's not going to be a solution. And anything you have like this here, where 3, -4, again, for the same reason, even though it's on the solid border here, it's also on this dashed border here. It's at the intersection point, and so therefore 3, -4 also would not satisfy this particular inequality, so it's not part of the solution. So that's the end of this demonstration about linear inequalities and systems of linear inequalities. Now please move on and do some of the examples that you see listed.